Yes, hello. My name is Kristoffer Nordvik, and I'm going to present a dynamic blade element momentum disk in OpenFOAM. So I'm a PhD candidate at marine technology here at the Norwegian University of Science and Technology. Content of the presentation: first, very brief background of my PhD project and linking that to this specific project, followed by some blade element momentum theory, and then I will go into modification of this existing rotor disk source, implying that it's already existing a steady rotor disk source in OpenFOAM. And then I will try to have a small demo of a tutorial case and end with some very brief notes about the way forward. So the background is we are trying to utilize pulse jet propulsion for a ship thruster. So we want to use or periodically vary the RPM on a ship thruster, so the RPM of a propeller, with the intention of obtaining these vortex rings, specifically this vortex ring formation, and then according to the existing literature, you could obtain increased propulsive efficiency. And then we want to analyze this in CFD with a simplified model, as it is more consuming to run with full geometry simulations. So the approach is this dynamic banked disk. The focus on both the project and the presentation is on the modifications. They're all, as I mentioned, it's already existing rotor disk source, so the reference for the original creator of that is linked here, and also a previous report in this project has also been presented. So for those interested, yeah, that's relevant material. Yeah, so starting off with blade element momentum theory, it's two parts. So the blade element theory is considering the propeller blade divided into sections, and for this specific case, we're considering this SINTEF P1565 propeller, which is an open access geometry. So if you look at the reference below here, you should be able to obtain the geometry. This is a model scale propeller with 4 blades. And then for this blade element momentum theory, the idea is to divide it into 2D sections, and then you obtain lift and drag coefficients for each section, and then you can sum them all together. So these are obtained from this boundary layer software called Xfoil, and then the result of that you see here. I should move this. Yeah, and then it's showing both potentials of without friction and also the viscous lift and drag coefficients. And as I said, we are doing dynamic operation, so then you could encounter rather large angles of attack. So then you may encounter stalling. So that's potentially a difficult challenge. And also with this 2D approach, you need to include some correction for 3D effects, so-called tip loss models. I will get back to that. So this is the blade element theory, and then the momentum theory is this control volume approach, which I try to illustrate here, where you have in viscous flow. Then you assume this infinitely thin disk where the force is applied throughout the entire disk. So it's essentially assuming infinite number of blades, and then you get a flow picture as you try to illustrate here with this pressure jump at the disk. Then you can combine these two to solve quite fast to get some initial estimate of a propeller performance, known as lifting line code. Here we want to utilize this in a finite volume method, so in OpenFlow. So the disk is no longer infinitely thin. We have a finite volume cell, and then essentially this disk is set up as a finite volume with a number of cells in the mesh, and then you need to calculate the forces in each cell according to this theory I just presented. So let's see if I can maybe add like do you see my marker? Yeah, anyone?
It's very small, but
Maybe now you see my marker?
very small. We can see it, but it's small. Yeah, it's fine.
Yeah, okay. But on the right here, you see I try to illustrate the flow at each cell. So the blue vectors here is the induced velocity from the force applied from this model. And then you also have the inflow U infinity, which would typically be the ship velocity, roughly speaking. And then also the speed of the propeller would contribute in the tangential direction as 2 pi Rn here. And then you need to include this correction, the T-plus model, and also this solidity factor, which smears the force out throughout the disk. Oops, sorry. Let's see. Okay. Yes, where are we? Yes, that was the theory. And then I will talk a bit about the modifications for this dynamic rotor disk source. So try to show the new configuration of the library here. The gray box on the left side is the original implementation, and then the new library is divided into a slightly modified version of that to allow for a derived class, such that this dynamic rotor disk source, which is this green box here, only contains the added modifications. Yeah, I will come back to this in the demo. Yes, and then I will not show all the changes here, but made some general changes with respect to code readability and moving some functionality from runtime to the constructor or initialization. A potential downside of that could be that you might lose runtime functionality, but at least in this scenario, I found it more reasonable to put it there, and also added some inline helper function. And then one main change is this solidity factor. So this is showing the applied force from a simulation after 5 seconds with a forward speed of 1 meter per second. And then I also included the propeller just for illustration. And then on the top right here, I've written out this solidity factor. So it's the ratio between the area covered by blades and the total circumference. Consequence of this is that it's not including distribution along the thickness of the disk. So as you can see on the figure on the right, the forces is only applied in one layer of cells. So as you refine this to a finer mesh, the forces will be applied to a smaller volume. So what I have done is that I've added the possibility to allow for multiple cells in the axial direction. And this is the same simulation after 5 seconds. So if we just go back there, you can see there are some pixel art. Basically, the simulation is not yet converged. So this is for a steady simulation, but here it's almost fully converged. But you see there is also some forces applied in this additional layer. Yeah, and just a note on that is the execution time was also reduced by a factor of 4 if you allow this multiple cell thickness, which is reasonable or at least intuitive from a numerical perspective. This solidity factor is now also moved to the constructor, so it's pre-calculated and not every time step or iteration. Second modification is this tip-loss model, which is now included as an abstract base class, such that you can select this tip-loss model in your case when you're setting it up, rather than changing the library, for instance. And I've included 3 different tip-loss models here. So the first one originates from this original rotor disc class, which is for a helicopter. So it is basically like a cutoff value, the given blade radius. And then this frontal, or also known as Glaubert's tip-loss factor based on potential theory, is included. And lastly, this Goldstein model, which is similar to the frontal, but here you have a lookup table based on the radius on your propeller blade and the inflow condition, inflow angle. Yes, and then the smallest but most important, at least in respect with a dynamic rotor disc, is that it now allows to have a time varying RPM specified. So it is now included as a function 1 object, which allows both analytical and also obviously a constant if you prefer, or you can also have time series specified as a table. Yeah, this is done in this add sub function, which will be essentially called in the momentum equation. If you, for example, the pimple foam solver, it will call this FV options, which will eventually end up here in this add sub function and add a force to this equation. So you see it takes in this linear system FV matrix as an input, and then it applies this force, which is found from this calculate function. Yes, and then this FV option that is configured with an FV option dictionary. So here I've mentioned the entries for the FV option, and also at the bottom here, these new modifications are highlighted. So the RPM is now have the possibility of a time varying RPM. And then you can also specify different tip-loss models, and this Boolean allow multiple thickness allows to distribute forces over multiple cells in the axial direction. So this is a new library, and then it needs to be compiled. As you see here, there are several files here included. I will come back to this in the demo in just a second. In addition to that, there's a tutorial case. So these files will of course be available in the course web page. So there's also a tutorial. This is an open water test scenario, which is a steady scenario. So first thing is that we do this steady test. So that's the tutorial case where you run different tip-loss model and can compare these to experiments. Yeah, and then the solver discretization solver settings is shown on the right here. These are also obviously found in the tutorial case, which can be run with some provided scripts. Yes, so then I was planning to have a small demo. So maybe you see is maybe someone can comment if it's possible to see the text there or if it's too small.
I think it's okay.
Yes, so in the provided files there are two libraries. So the source code is in this FE option by root of this source. There it is, you will find this README, which briefly describes what it is and also how to compile it. So first you need to source OpenForm, and then from this directory you compile it with this vmake, and then optionally it will be clean up temporary files. So while this is compiling, I'll look at the source code here. So you have this my router disk source, which is the original class, you could say, and then you have a derived version here, which is this dynamic router disk source, and also this T+ model is included here. So in the constructor, for instance, now you will find that it calls this read function, which reads in all the dictionary entries, and also the solidity factor here is now calculated here. And then I mentioned this add sub function, which is essentially what applies these forces, which will call this calculate function. That is found in this templates.c file here, and this is where the blade element momentum theory is basically done. So as you can see, you look up your blade configuration for each cell, and then you find, for instance, the inflow angle and angle of attack. Then you get some lift and drag coefficients, and here you see this T+ factor is now found from this T+ pointer, so that is pointing to this specific implementation of the base class you have chosen, and returns this T+ factor, which is the function that calculates this. Yeah, so now, yeah, then eventually you modify this force value here, which is what is changed in the momentum equation. Now we'll go over to this tutorial folder, which is also located in this tutorials dynamic router disk. Here you have these all run scripts, which you can specify some parameters you're running in parallel. And also if you want to run with a coarse mesh or a finer mesh. So let's say you want to run with a coarse mesh, then you have these forward velocities, which is different forward velocities you would run. And then also the T+ model, and that you could specify when you're calling the script. So if, for instance, we want to run with this step and the Goldstein, we can run it like this. Then you would see printed out the refinement settings. Since it's a coarse mesh, these will be changed in this snappy hex mesh, which is what it's using for generating the mesh. And then the simulations are set up in this results folder, where it will run each simulation according to what you have set up. So if you look in the PeopleFoam solver log file, you would see now that you have this FE options log here, which prints out some information about your disk. And when it starts running, you see this typical PeopleFoam iterations, but also there is some additional print of the dynamic router disk. Yeah, so now if I go back to the presentation, then while this is running, so the mesh which will be set up is looking like this. So you have a cylindrical domain with an inlet and an outlet, and then you have this no-slip patch cylinder around, and then the disc is in the center. And the propeller here is also just for illustration. And then here is an example with this coarse mesh. After the simulation, there is this post-processing script which will plot this open water diagram, which includes experimental results, which is these sticker lines, and then these finer or dotted lines are for simulations with a finer mesh. And then you have these scatters, which is the results from the simulation. And as we can see here, the coarse mesh is not very accurate, whereas the finer mesh is rather accurate, specifically for the frontal and the best for the Goldstein T+ model. Yeah, so this was for the coarse mesh, and then similarly for a finer mesh, then you see this match. This is the fine mesh, so then obviously the results match. So these finer lines are also provided in the tutorial case. Yeah, and on the left here you see the streamlines, including the swirl added by the disk. So this is for a simulation of 1 meter per second with the frontal T+ model. See over time. Then if we now go back to the simulations, you now see that we have 2 folders from both simulations and this folder. So this is the results from this coarse mesh simulation. And yeah, similar as I showed in the PowerPoint, they are not matching very well with this coarse mesh. But if you were to run with a finer mesh, you should get better results. And then similarly, as you typically do, you have this all clean script, which will clean up the case back to its original state. Okay, and then this is a dynamic blade element momentum disk. So as of now, we've just talked about this steady state. So you could add a time varying RPM by doing these modifications here, specifically in the FV option dictionary, and then you, at least in terms of generating these vortex rings, it's better with a small or towards zero velocity. So reducing this for velocity towards zero is beneficial for vortex ring formation. And then you remove birch rights such that you get all the time steps you want to see the transient behavior, and then you should be able to see these vortex rings. So I have an example with this finer mesh with this sinusoidal, and then you see the vortex rings here are illustrated with this Q criterion, and then you have these arrows is showing the applied force. So this is also showing the unsteady or time varying operation. But however, as in future work, the current model is a steady model. So even though it's able to run unsteady, it's not modeling unsteady operation. So incorporating this unsteady lift is a very important next step in this project, and it's not totally clear how we should go about this, especially regarding these memory effects. But that is the way forward, and then we also have unsteady experiments which we can use to validate the model. Okay, so yeah, I think that was it. I guess if anyone has